Let me show you why log base a of x times y is log base a of x plus log base a of y. Okay. And I'm going to prove this. It's like solid mathematical proof, okay? Which I seldom do. But here, this is a really serious mathematical proof. And that means if you can actually understand this proof, that means you're pretty good. Okay, so think about this as a challenge. Right? Okay, so I start from the left side, and I'm going to eventually show that this is equal to this right side. Okay. Okay, here's my reasoning. First, x is a to the log base a of x, and then y is a to the log base a of y. Looks crazy, right? But do you see that these two are equal? Why are they equal? Why are these two equal? What rule did we learn about cancellation? If you have a and log a, what happens? They cancel, right? If you cancel this, what do you get? You get x. So it's this thing is the same as x, right? If you cancel a and log a, what do you get? Y. So it's the same thing as x times y. Good? Right. So it's like you take a medicine and it gets worse before it gets better. Right? It gets like painful in the beginning. Now it's going to get better. Okay, so this is the worst format. It's going to get better. Okay. Now, if you have the same base and you have exponents, what's the rule? If it's same base, what do you do with exponents?
The base is the same, you
Add the two, exactly. So you write down log a of log a of x plus log a of y. Okay, so that's the second step. And now, do you see anything canceling here? What can you cancel? Huh? This a gets canceled with what? This log a. Yeah, those cancel, right? What are you left with? Look at that, right? You actually understood the mathematical proof. That's the mathematical proof. 3 lines. That's all you need. That's the proof. Now you can do the same exact steps to show that division becomes minus. It's almost the same. The only difference is because you have x divided by y, you have this division, and then when you divide, you keep the base and the exponents you subtract, and you end up with a subtraction of 2 things. That's how you prove the second thing. Now, what about our favorite frog over the log rule? What was the frog over the log rule again?
The c goes to the front of the log.
Yes, yes. Log a of x to the c, this exponent inside, it jumps over the log. And that does that. Okay, so that's the rule. I'm going to prove this. Let's prove it. Okay, proof. I actually wrote this 5-letter word. Proof. Right? This is, you start from log a of x to c, and I'm also going to make this thing go worse before it gets better. So x is a to the log base of a of x to the c. Okay? And as before, a and log a, they cancel to give you x. So it's the same thing as before. Now, what's the rule when you have a to some power and then another power? What's the rule? You multiply m and n, right? Same thing. So what should I do here? That's log of a, this times this, right? Now, multiplication is commutative, so I'm going to write this times this. I'm going to write c times log base a of x. Okay. Now what cancels? What can you cancel? A and log a. What do you get? That's the proof. Now the proof of the base change formula is a little more involved, so I'm not gonna do that. But once you see these proofs, there's one thing that you start understanding. Where do these log rules come from? Are they some arbitrary rules that mathematicians made for you? Yeah, but it's not. All rules come from somewhere. Especially the log rules come from where? The exponential rules. Okay? So all the exponential rules that you know, it gives you some rule for the log, and the reason for that is because logarithms are inverse functions of the exponential function. So anything that exponential functions enjoy, there's some kind of some correspondence in the inverse function world, and that's why you get all these strange looking rules. Okay, so we're gonna start doing a lot more examples using these next time.